All right, now we're at step 3, doing the computations. So again, this is this smoke detector problem. We've written our hypothesis statements and we've checked the conditions. So now we can create a normal model of what we would expect of a sample taken from this city. So this is where the rubber meets the road, so to speak, or you might say where the sample statistic meets the hypothesized model. So what that means is that we have, let's do a picture first. So one of the keys is that you do need to draw a picture. Okay, so I'm just going to go ahead and sketch out the normal model. Okay, like this. Get it to kind of come down. All right, so what this model is that this is a model of the hypothesized value. So again, the null hypothesized implies the model. The model is what we would expect to find, where would we expect to find p hat if we sampled from the population. So we would expect the center to be at P. That's what we hypothesized, right? We said that the center of the model would be 90. Now we checked all the conditions so we can use the normal model. So what that means is the standard deviation for our model, okay, so we call it standard deviation of P hat, where we would expect the sample to come from. So sometimes I like to put P hat right here to kind of the same way we do with a Cartesian coordinate system. We say y and x. So this would be P right here, like x. Okay, that's the variable that we're measuring. And so we expect it most of the time to land right in here. So since the model is an extension of the null hypothesis, and the null hypothesis says the center is at 90, then that's the value we use. We use PQ over N. Okay, and that's the square root of 0.9 times 0.1 divided by N. So what a typical error is that students will use P hat and Q hat here. Okay, so that's why I'm working so hard to sort of make the connection. So I want you that this implies that the standard deviation of the model is PQ over N, the hypothesized values. Sometimes some text will put a little 0 right there on P to make sure that you know that that's the hypothesized value, and then they will actually put a 0 here and a 0 here to remind you that we're going to use the hypothesized values. Okay, so what I get is 0.015. Okay, so now I know, and it's not necessary. If you have time, it would be nice, but it's not necessary to label all of these. This would be 0.93, right? And this would be 0.915. Okay, so this would be 0.945. Alright, so this is our model. This is where we would expect P hat to fall, somewhere in here. Now, recall that I'll just do it again, that N is, I should have written it right here. Let me cut that out and say 400. So N is 400 and X was, what was it, 3 something? 376. 376, and then so P hat is 0.94. So we can kind of go over and see that 0.94, it's going to be right about there. P hat is 0.94. Okay? So, we're interested in, we want to use the model, what's the probability of getting this value, this p hat, given HO is true. The null hypothesis is true. Okay, well, so you write that. What's the probability that p hat is greater than, right, greater than 0.94? That's what we're interested in. Okay, so you need to do your z computation. So we'll just do that over here. Remember that z is equal to the observed value minus the mu divided by sigma. Okay, so for this model, the center, mu, is 90, and the standard deviation, sigma, is right here. Okay, and then the p hat is the observed. Okay, so we're going to have 0.94 minus 0.90 divided by 0.015. That's going to be our z value. So I'm just going to rewrite it here. Z greater than 0.94 minus 0.90 divided by 0.015. That's equal to P, the probability of Z greater than, and I get 2.67. So Z is equal to 2.67, and that looks about right, right? Because that's 2 standard deviations and a little bit more than half. Okay, so our drawing's reasonably consistent. Okay, so now that's just going to be normal. C, D, F. You can also use the back of the book. So we're going to go from 2.67 to infinity. Okay, and I get, what do I get? I get 0.004. Okay, so I can come up here and let's see, to the model, you might want to say 0.004 for the area, and I think we're good. Alright, so now the next video I'm going to use to interpret this result. Okay, so these are the computations. So it's combining both doing a picture and showing your work. Alright.